Hey everyone. It is such a pleasure to be here with you today. Thank you for sitting through my talk. I know you've already seen a lot of incredible stuff today, and I will do my best to keep that up. I am here to talk to you today about a project of mine called Wattwiser. But before I give you a lot of details about Wattwiser, I want to tell you its story. Why? Because its story begins here, or really here, but last year, at the 2023 Ubuntu Summit in Riga, Latvia. You see, I came to the 2023 Ubuntu Summit, and at the time, I'm a professional software engineer, and I was experiencing incredible cognitive dissonance, because while I was looking out at the world and observing a dramatically worsening climate crisis with extreme weather events and acidified oceans that dissolve shellfish and a lot of bad going on in the world, I looked at my own industry, right? Working with computers and building software, a thing that I love doing, and it felt very disconnected. It was unclear how these two things related to each other, and I could see the waste that was happening in my world. And it wasn't clear to me what the right path forward was in order to integrate these two things that I care a lot about until I came here. And I saw these amazing talks. It was Framework and Fairphone first, who showed this completely different paradigm for building electronics, right? They showed that, no, it's actually possible to build devices that are going to last you a decade or more, right? Where if something breaks, you replace that piece and not the whole thing. That was something that had always seemed like it would be great to have, but I realized the future is now in that case, right? It's already here. They're already doing this incredible work. And that gave me a lot of hope that someone was already out there solving some of these problems. And then I saw the KDE Eco Initiative's presentation on other problems in our sphere, on the incredible cost of fabricating new hardware that dwarfs the rest of the hardware's lifespan. I mean, we make CPUs at the nanometer scale now, or a few nanometers. It's incredibly difficult to achieve that kind of precision, and it uses incredible resources. And the carbon dioxide emissions associated are correspondingly enormous. And at the same time, we throw away a ridiculous number of devices, and that has all kinds of downstream effects too. So it became clear in those conversations that we have some big problems that we need to grapple with as an industry if we want to figure out sustainability and get the future right. So the key problems that we seem to need to address are finding ways of using our devices for their entire useful lifespan instead of just upgrading on some fixed 3 to 5 year cycle, which is sort of the norm, right? Server cycle in like data centers, they get rotated out every 5 years, and I think some data centers may have moved to 6 recently, which is an improvement. But we need a more radical way of ensuring that hardware that is still very useful and was very expensive to create remains in use. And on top of that, we're seeing right now an incredible surge in what it takes to run our computing infrastructure. AI is energetically expensive, and I think we all know that, but it has use, right? It provides utility, and we need to find some sort of balance there in order to figure out how to make that technology actually a sustainable thing for us to engage with. And a lot of that starts with observation, with measurement. How do you quantify it? Because you can't improve anything until you can measure it well. So I thought a lot about these problems in the time after I left the last Ubuntu Summit, and it seemed to me that there was actually something we could do that would work on both of them at once. So, what drives the demand for using energy in the first place? Energy, according to physics classes, is the capacity to do work. And in the classical physics sense, that's kinetic, and that's applying a force to a mass, right, to move it around. But in software land, it's flowing current through a circuit inside of a processor. So in our world, activating parts of the CPU, energizing circuitry, is the thing that consumes energy. And if we can find formulations of our workloads that activate less circuitry, that achieve that same result by doing less work, using less energy, it has enormous benefits beyond the obvious, right? We know that it would drain our battery less. We know that our computer would heat up less. We know that our data centers would be cooler and consume less power. But it actually goes beyond that, because doing less work also extends the backwards compatibility of your software. You're demanding less from the hardware, and so the previous generation of CPU and the one before that actually stand a chance. Optimizing along this axis drives change on both of these major sustainability problems. And so I was thinking about this, and I wanted to engage creative and brilliant minds other than me, because I'm actually not that smart, and I would love to see what people who think in a not linear mathematical way would do with this problem space. So we launched, me and a couple of collaborators, the Wattwise Game Jam. A game jam, if you're not familiar, is like a hackathon, an event where you rush kind of to produce software under some fixed timeline. But instead of making general purpose software, you're creating video games from scratch. And the video game community, especially the indie game community, is full of brilliant, creative minds who both have intense technical knowledge and artistic vision. And I hoped that by bringing this question to that group of people, we would arrive at fascinating and innovative answers. But we had to enable people who participated in the Wattwise Game Jam to actually assess what they were building for energy use, because we were challenging them. How do you make the most fun for the least power, right? How do you balance those factors? And they have to be able to measure that. And so we set out and we thought, okay, it'll be easy. We'll just point them at a software that lets them measure the energy consumption on their device, right? No problem. And those softwares do exist, but we ran into quite a few challenges. Because we were targeting indie game developers, the two platforms that we thought were the most relevant were Windows and Linux, and almost nothing supported both of those. But it gets worse. A lot of the software only supported time windows of something like 1 second or larger in granularity. So you could find out, yeah, great, during that 60 frames, I used this much energy, but like which frame, was there something in there? Was there a spike? And what was I doing during that time? It's impossible to answer questions like that with such coarse data. So we needed more granular data with better platform support. And then we were talking about video games. We were talking about a graphical workload, but most of these tools didn't support GPU data or only supported one vendor. So it was clear that we needed a more holistic approach, and we started building one. And that's the Wattwiser project. That's what I'm here to show you today. But as we built it, we realized, hang on, there's actually nothing we're doing that's specific to video games. Our workloads that we run in all domains of software engineering, they're running on CPUs, they're running on GPUs. AI runs on GPUs, graphics runs on GPUs. We can use this for everything. And so we decided that maybe we should target that. Maybe we should be more of a general purpose way of assessing energy consumption. And so what is Wattwiser? It's a software stack that can run on a machine, query it for energy data from sensors that are already inside of it. CPUs for the last 15 years have had good energy sensors built into them. And GPUs frequently have good ones also. But this data is like frustratingly difficult to access. So Wattwiser gathers that data from a variety of sources. For your CPU data, we rely on a technology called RAPL, the runtime average power level, that Intel and AMD both implement. And that gives us very reliable estimates of what the energy consumption of the CPU is. On Linux, this was a dream. On Linux, if you just look in the sys file system, there are files. And if you cat them, they give you the readings from these energy sensors. It's mwah, it's beautiful. On Windows, there is no facility whatsoever to access this data. So an excellent other open source energy monitoring project that's focused at sort of monitoring a fleet at scale addressed this problem by writing a Windows kernel mode driver that just does this. It just accesses a handful of MSRs in these CPUs and surfaces them in a user space API. And so we were able to do that and help them fix a problem with supporting AMD CPUs in the process. On the GPU side of things, we're very fortunate because, again, on Linux, it just shows up if you have an AMD dedicated GPU. It just shows up in libsensors in the hardware monitoring systems of the kernel. It's beautiful. It's easy. It's wonderful. The real message here is that Linux is great. And NVIDIA, even with the proprietary drivers, provides this library, the NVIDIA management library, that can give you this data richly easily. On Windows, the picture's a little more complicated. AMD has a different management library that you have to use. And for Intel integrated graphics, because that's actually part physically of the CPU die, you get that data from RAPL also. The jury's still out on Intel dedicated graphics cards, but my friends at the OpenVINO booth assure me that they're trying it, so I'm waiting to hear that maybe tonight. And we can also read your battery. So what do we do with all of this data, and how do we make it useful to you? Well, we aggregate it into this deeply proprietary format that no other tool supports. It's called comma-separated values. And it's deeply cryptic, as I'm sure you can see here. We have a few fields. Every sample that we read has a start and end timestamp to the nanosecond scale. And then there's a column for every sensor that we found, which provides the unit of that sensor. Sometimes we can find sensors that directly measure energy, and those are measured in joules. Other times we find power sensors that we'll just integrate ourselves to determine the area under the curve and give you joules in an interface. But we chose this format because it's really, really easy for you to use the tools that you already know how to use to do your own analysis. We're not interested in being the only way that you monitor power or that you introspect this data. So we do provide an interface for introspecting this data because I don't actually know many tools that ingest CSV data live and visualize it. I'm sure there are some, but we wanted to be able to give you a sort of a high-quality way to look at this that's domain-specific. And so we built the Wattwiser GUI. So here you can see a graph where the y-axis is wattage, so that's the rate at which energy is being consumed. And the x-axis is time with more recent data on the right. We get a line for every sensor that we detect. And in the table at the bottom, you can get the names of the sensors as well as the cumulative energy consumption we've seen since we started measuring. And so this facility allows you to see in real time what the machine you're monitoring is spending its energy on. And because the data sources that we have can be quite granular, we can see the CPU and the GPU workloads separately and their energy consumption separately. You can actually have a lot of fun just launching different applications and seeing, hey, how do they tax my system, and where does the energy go when I run this? But that's just sort of surface level monitoring, and it's nice to be able to see this. But if you actually want to improve things, you want to optimize, you need something a little better. So we also offer a benchmarking facility where you can point Wattweiser at an executable, and you can say, hey, what's the energy impact of running this process end to end? So when we try and assess that, the very first thing we do is actually nothing. For 2 whole seconds, we just do nothing, and we monitor the energy consumption of the system during that time. We establish a baseline. Then we launch your process, and we continue monitoring until it exits. And then we take a second system baseline afterwards so that we can know how consistent our system baseline is both before and after your workload. And then we present you with a lot of information about what we saw during your workload and which sensors registered how much energy change. And we'll factor the system baseline energy consumption out of the data. We give you the ability to see both. But so in this particular case, I've had Wattweiser measure the energy consumption of its own CI script. But the first time I ran it, we had a cold compiler cache. Everything had to be built from scratch. All the tools had to run. And so it uses, I believe, 1,100 joules total. But the second time, because we have a hot cache, it only uses 14. And you can see that in this graph below, where we're seeing both data sets from both runs compared together, where their start times are aligned to each other. So this big boxy wave here is the energy consumption of the CI actual workload. And then down, just hugging the x-axis, there's this little sawtooth thing going on. And that's the workload where it's just discovering that the cache is already hot and it doesn't have to do anything. And so this tool is designed to enable you to optimize your workloads along this axis. And there's a lot, it's easy to do. We have like binary releases already. Now you'll note that there's a sudo on this screen. And one of my goals in coming here was to get the help from the smart people I know are at this conference to remove that. RAPL's energy data is so granular that it was discovered to be a cryptographic side channel. You can exfiltrate secret keys that the CPU is manipulating by reading the energy sensors. And the Linux ecosystem solution to that problem was to make it require root to read the RAPL energy data, which is fair enough. I mean, you don't just give root out for free, we hope. But I would love to find a much more ergonomic and equally secure way to manage access to these sensors. So if you're in the systems programming and security space and you want to talk to me about the cool distribution features that we can take advantage of to do some least privilege here, please, please, please do that. But anyway, you just run the Wattweiser sensors, regrettably, right now as root, and they'll spit out the CSV data that you saw earlier, and then you can, send that to whatever analysis you want, but one option is to pipe it into Wattweiser proper, the GUI, where you'll see the interface that we've just described. Or you can just run Wattweiser against a existing CSV file if you want to explore it in the UI. So I invite you, please, to try this out on your own machine. Sustainable software represents a real opportunity right now. There's growing concern for the fate of our planet and for sustainability in general. And that is felt both in the zeitgeist, but also in very real business considerations. Governments are adopting standards that require sourcing eco-friendly and sustainable solutions, things that are validated to be eco-friendly and sustainable, and you have to demonstrate why you couldn't. You have a burden of proof for why you didn't source the software that has evidence that it is eco-friendly and sustainable. That represents a real opportunity for businesses but also you've already seen the other benefits that we have. We're going to reduce energy consumption. We're going to enable devices to last longer. And those things really matter. So I challenge you to try it out because I would love to know whether it does work on all of your devices. We've tested it in a lot of places, but there's way more diversity of hardware available to you than there is to me. We could also really use support adding sensor data for devices you care about that we currently don't know how to interrogate, because there's quite a few of those as well. We would love to get rid of that ugly sudo thing, and I bet there's a convenient combination of systemd features and like a one-time sudo operation that would smooth the whole thing over. I just don't know the incantation. And there's a lot we could still do. There's a lot that we could do to integrate this directly alongside profiling and tracing software that already exists, so that you could see your energy data and your call stack in the same UI. You could say, wow, there's an energy hotspot here that is just massive. What was I doing, right? And the answer would just be right there. And that's like on the table. You could already achieve that if you were willing to do a little scripting work to collate the timestamps of our samples and the timestamps in your profile, because they're both using the same high-resolution clock anyway. So with that, thank you very much for listening to me. You can find resources about Wattweiser, these links here. This QR code will take you to this slide deck so that it's easy to follow the hyperlinks. You can also contact me directly. My email is on the slide. And my collaborator in the Wattwise Game Jam, Andrew Thorpe, who designed the cool logo you've seen, can be found at that GitHub link. And the other open source energy monitoring solution, Scaphandra, that solved the Windows RAPL data is linked there, as well as the RAPL driver. So thank you very much. Are there any questions?
I recently bought a hybrid pickup truck, and I joined the Reddit group for that pickup truck, and I noticed that people with the same truck were posting screenshots of their efficiency on the dashboard. It would tell you like how many electrical miles you drove and how much your miles per gallon was. And it struck me as interesting that people, they want to compete for efficiency, and I think part of that is due to wanting to do, everyone wants to do their part to try to make things better. In terms of your project, it seems like higher order things could emerge from knowing more about how energy is used in a computer. Do you see gamification or kind of tribal emergent things coming out of being able to measure energy at that level and being able to report it?
I could see an amazing future where software projects compete along this axis. I mean, just imagine for a second that we could stand here and say, we have the data to say that Ubuntu Linux is the most sustainable, energy efficient distribution across these ranges of hardware, and we can prove it, right? That's a big thing to be able to say, and we have the tooling to assess that now. I have not done a comprehensive study in that area, so we can't say that. But I think competing for efficiency is both something that we can do and something that I would love to see, because it has wonderful side effects. It makes the world a better place, and it brings people together. It gives us something to work toward, and we can achieve incredible things when we have that sort of shared vision.
Hey, great talk, thank you very much. I was glad you mentioned other observability kind of metrics towards the end. I was thinking on the way through, an interesting direction might be to have something like a Prometheus exporter on the grounds that your exporter can be written in anything you like. Ultimately, I've seen them written in Bash and Python and Go and Rust. But that is something that you could easily confine within a systemd unit with just the privileges it needs, but also you then for free would get all the benefits of something like Grafana and that direct correlation, right? Grafana specializes in kind of displaying time series data, And is that like a direction that you've considered, or something that it just seems like something that if you had it running on the machine all the time and it could just be scraped by the thing that wanted to understand what was going on, that might be a nicer way of presenting it.
Yeah, I think that there are interesting synergies with existing monitoring stacks, and we could export something to, say, Prometheus, but at the time scale that we're working with, where we're sampling every 10 milliseconds by default right now, and I would like to actually get that lower, because I think we can make some intelligent decisions and drive that down even lower. Involving the network introduces a lot of unpredictability, and we have to start choosing, okay, who or what or when is going to maybe get blocked by interacting with the network, or what are we going to do when the network side is slowing us down? Are we going to drop samples or whatnot? Whereas this particular approach was pretty focused on the idea that you're on your development machine and you're optimizing the project that you've been working on in order to assess it. But I guess, yes, I think we can do that. And I would like to try, and I would like to see what that's like. Because you're right, Grafana already has great capabilities for visualizing this data. And it should actually be pretty easy to mesh them together.
Great, thank you very much.
Hey, Chris, thanks so much for the talk. It was both very, very clear and also quite inspiring. And I loved how you framed it at the beginning in terms of the cognitive dissonance between caring about something in the world and then also feeling part of this industry that in many ways is part of the problem and wanting to do something about it where you have some agency to do that. Which leads me to the question. So you have this idea, it looks fantastic. You're essentially one guy with this brilliant tool looking for a way to push that out. What could come next in terms of community engagement, whether that's people here making software, people making hardware? How do you get this out to kind of find that broader reach that it clearly needs to have an impact?
Well, one thing that we've already done is we've released this project into the public domain, because our goal here is for this capability to be used. So we would love for anyone to see exactly how it works, even take this implementation if they want to, and apply it within their domains. But more broadly, we would love to see software projects come alongside us and say, you know what, it would actually be really awesome to be able to quantify our own workloads. I've been talking to some of the wonderful projects represented here today about doing that very thing, about saying, okay, can we actually measure the energy impact of our really common use cases? And what does that look like? And what does it look like when we optimize that over time? And how cool is it to be able to show, you know, we actually are the most efficient way to do this thing, you know, when we do a fair comparison against these competitors. So I would like to see projects adopt this, and I would like to see growth in the capabilities of the tool. I would love to work on this stuff even more. This is my hobby project, but if any companies wanted to actually engage with this really directly, I am freelance, and I would be happy to help them on that journey.
Awesome, thanks.
Thank you very much. If somebody doesn't really care about performance or the reliability of their software, they're made to care because the market punishes them for not caring. But at the moment, we might care about energy use, but nobody will make us care if we don't.
Yet.
It has to be a little bit systematic. How can we make it more? We're not the government.
Right.
But on the other hand, we might have some influence maybe at an operating system level or some other level. How can we push it up so that there is not, we're not just relying on people's goodwill, but there is real external pressure?
Well, I think I really appreciate the question, but I do think it sort of translates into how do we change the law? right? And that's a question that we ask quite often about a lot of things. And it's domain specific. But I do think that there's a few things to keep in mind that part of changing the law is changing the culture. Part of it is making sure that the people who make those legal decisions know what's important to their constituencies. And so thinking about this stuff and talking about it and sharing that in a forum where it'll be heard is a big part of that. And I live in the United States, and so it's difficult for me to offer a global perspective on changing the law, because I frankly don't know how it works in many of your home countries. But at least in where I live, a lot of laws are actually drafted by ordinary people and then submitted to their representatives and debated and revised and passed. And so politics is not a spectator sport, much as news seems to portray it otherwise a lot of times. So we have the agency to propose that future and ask that it come to pass. And so I think we can drive that change in our own homes and at our local scales.
Thanks very much for the presentation. I'm curious about the granularity. You said that it's very, very fine granularity from a timing point of view, but it seemed to aggregate CPU as one thing. Is there sort of per core information? How does that get in? How much detail can you get with the current sensors?
So it is hardware specific what we get, and Intel and AMD are subtly different in how they present that information. The graphs that I showed today were from my 2016 Intel i7, so it's a 7th generation core. We're on what, 14? So things have changed quite a bit. It only has one processor socket. It only has 2 physical cores, and 2 of them are hyperthreads, so you see 4. But in my model, what we get is deaggregated into core activity, energy consumption for memory purposes, keeping the bits fresh in that storage medium, and then something that Intel calls uncore, but loosely translates to everything else on the die that isn't those 2 things, including the integrated GPU. On other models, I have seen much richer data coming from these sensors. So for server class CPUs, you actually get a lot more individual data streams that you can look at. And I had a great conversation earlier today, or no, sorry, it was yesterday, with some folks from AMD about how there's actually even more granular data that exists within the processor about this, and that we might be able to actually access. So I guess to your question, it does depend on what the hardware is. And I think there is still even more granularity that we can unlock in dialogue with these vendors to actually know how it all works.
Thank you.
Thank you.
Thank you also for the talk. And I found it very interesting. As a software developer, I think it can be very fun to try to optimize things, and now thinking of this new dimension of energy consumption. And I imagine that throughout the development of this tool, you must have measured the consumption of many applications. And also, you mentioned the Wattwise games. Do you have any interesting results that you got measuring many applications, or from the Wise games that you mentioned?
So,
we're totally fine to continue that, but it's break time. If you need a break. See you at 4:30, or stay here and continue with Chris as long as you're happy to. You have about 25 minutes if you wait for the next session, okay. Or you take a break. So just want to mention, but yeah.
I did have a frenzy of measurement when we first developed this. One of my earliest observations was I sometimes play some video games with my friends, and graphics settings have a just unreal impact on energy. It's not necessarily the game. The game makes a lot of style choices that affect graphical energy consumption, but the difference between ultra and high and medium and low is quite striking. You know, you can take my desktop computer, which is also about 8 years old, I think, and it'll idle at 20 or 30 watts of energy consumption. But you can make it use 250 if you push the graphics envelope all the way up. And that's not even taxing the CPU all the way. That's just a large, like quite stressful GPU workload and a moderate CPU one. So it can go worse. And you know, I do not have the latest, greatest, I've kind of lost track of graphics cards a little bit, but imagine the really good one right now, whatever that is. I suspect that it is quite expensive if you tax it all the way. And so I think there's an interesting question we need to ask ourselves here around, you know, how we choose to spend our energy and what's worth its price. And I wrestle with that. You know, if I want to play a game with my friends, it's like, well, I have a whole rainbow of options of expense before me, and where do I want to fall in there? I also found that like messaging applications, you know, simple ones, right, where you just send and receive messages with the communities you care about, the energy differences between them are unreal, folks. I invite you to measure for yourself, so I won't name any names, but chat it's just striking. It's striking, the differences that the technologies have. Yeah, is that?
Yeah, thank you. That's very interesting.
Thank you.